Now, I want to emphasize here that when you're performing a double integration over, say, a particular rectangle or something, sometimes instead of writing the actual limits explicitly as a shorthand, we will just put as a subscript down below R, standing for rectangle, or, as we'll see in just a little bit, a more general region than necessarily a rectangle. But the rectangles are the easiest ones to integrate over. F of x, y, dA. This is what will often be written here. Now, we're writing dA because we're thinking of this as what? Differential area, okay? The limit of what happens when you're doing what? You're partitioning R into a bunch of subrectangles and then taking the limiters, the norm of the partition that we mentioned previously, goes to 0, okay? So what this effectively is just saying, you could be going dx, dy, or dy, dx, depending on which way you want to integrate, in the y direction first or the x direction first, okay? Now, something I want to emphasize just here right off the bat is, here, this f of xy, we could always interpret this as a volume, just like we did in our previous example, but that isn't necessarily the natural interpretation in some cases. For example, suppose f of xy represents, say, a mass density. Okay, if f of xy represents mass density at various points in some sort of thin laminate or thin plate, when I go dA times f of xy, what I'm actually finding then would be what? Differential mass for that little subrectangle, all right? Then I'm adding all those up. I'm actually doing what? And taking the limit as the norm of the partition goes to 0. I'm actually would be finding the mass of the entire thin plate, okay? So it isn't necessarily the case that we always naturally interpret a double integral like this as a volume. Sometimes it has a very different interpretation, okay? Could be an energy, a mass, whatever. Okay, all kinds of different things. But volume is a good geometric interpretation to begin with here. Now, first thing I want to say here, integrating over a rectangle is basically easy as far as the setup goes, okay? If you're integrating over a rectangle, which we will still call R, okay? Now R is this. I don't know if you guys understand this notation, but look it up. This is the Cartesian product of you set up all values of x going from a to b, y goes from c to d. So this is exactly the rectangle we were looking at before. This is just the set of all ordered pairs where x comes from the interval from a to b, and y comes from the interval c to d. There, I've defined the Cartesian product. Okay, so if you're integrating over a rectangle like this, we've already seen this. You could go from what? A to b, c to d, f of x, y. Okay, now wait. The c to d here is actually what? That's referring to y values, right? Okay, y values. So here I'm integrating out y first, and then I'm integrating out x. Or I could turn this around very simply and do the following. Maybe I would rather integrate in the x direction first. So then you guys see my inner integral. I'm actually integrating in the x direction first. Therefore, I have dx. And then once I'm done with that, I've got whatever that result is, which is going to be what? In general, a function of y. Then I would integrate that out from c to d. Okay, so this is the idea, what I'm trying to get at. Changing the order of integration over a rectangle is absolutely easy because the limits of integration on both integrals are constants. Okay? This will always hold for rectangles over the Cartesian plane. This will always hold for rectangles. but it only holds for rectangles. If you're integrating over some region R, which is not a rectangle, at least one of these inner limits is going to be a variable. It's going to be a function, okay, not just a constant. So keep that in mind. So I'm going to do an example of this in just a minute. Now, there's something called Fubini's theorem, which says that you could do what? You can always evaluate a double integral that we've just defined previously by performing an iterated integral. And you guys can read about the details on that. But you guys will see here some examples of this where I want to set this up. Now, you guys have to, if you're not setting up your integral correctly from the beginning, your double integral, you've already shot the problem. You've completely blown it. Okay? You've completely blown it. So you've got to get the limits of integration right. Okay? So right now, I'm interested in making sure that you guys set up your integrals correctly, not evaluating them at all. In fact, I'm not even going to give you an integrand here. It's just going to be, well, I'm going to give you an integrand. It's just a theoretical one, f of x, y. Okay? So we're not doing calculations as such. We're setting up our double integrals as iterated integrals. Okay? This is how we're going to do it. Now I'm going to take an example. Okay? This is not going to be a rectangle. Suppose I have the line y equals x. We all know what that looks like here. All right? So there I've got it drawn here in the xy plane. And then I've got a vertical line, which is the line x equals 2. And then I have one other line here that's already drawn, actually. It's the x-axis. Let's go ahead and write its equation, y equals 0. Now, my region R this time is going to be this triangle, not a rectangle. This triangle, not a rectangle. All right? How are we going to set up the integral to find this? Okay? So this is R, everybody. You understand that's R? Okay? F of xy, which I said I'm not even going to give you, because I'm not interested in specific calculations. I'm making sure you guys can set up the limits of integration properly when you're dealing with something other than a rectangle, which is always easy. Okay? Because, like I said, if you can't do this, you can't set it up properly, nothing else matters. You pretty much shot the problem. This is 2. It looks like z. But you guys know I cross my z's all the time. Anyways, there it is. Let's talk about this. Now, I'm going to go ahead and integrate in the, just for kicks here, I'm going to integrate in the y direction first. Okay? And then I'm going to turn it around. Okay? Now I'm going to integrate in the y direction first. Here's what I'm going to do. I'm going to imagine in my mind that I've done what? I've partitioned up the x and y axis. Okay? Now I've got to partition a little differential change in x here. Okay? And then I'm integrating in the y direction first. So do you guys see I'm forming these little sub-rectangles, but I'm interested in going in the vertical direction too. Yeah, this makes like a little picket here. Yeah, there's pickets, there's more of them here, right? I'm not going to draw them all in here. That's not going to be helpful for you. I could draw a whole bunch of little pickets here, just like this thing, right next to each other. Okay, not a good thing to do. Okay, that's not what I'm interested in right now. I want you to think this way first. Okay, I'm going to integrate in the y direction first. Okay, I have f of xy. I'm integrating in the y direction first, so I've got dy dx. So far, so good. Okay, now what I'm going to think about is I've taken a particular value of x here in this, this subinterval. Okay, I've got an x sub I there. It's fixed. Okay, and then I'm going to be taking sample points in each of these subrectangles here. Okay, and then I'm going to take what? The limit as the norm of the partition in the y direction goes to 0. And that gives me this inner integral. Okay? Now, wait a minute. Look at the limits on y. Where is y starting here? Well, y starting down here at the x-axis. That means it's starting at y equals 0. Okay? Now, later on, I'll just be writing 0, not y equals 0. The fact that it's y should be obvious, but I just want to emphasize. And then, people, where is y going from and to? Some people tend to think this. Well, hang on a second. I'll take, let's see, the corners of this triangle are what? 0, 0, 2, 0. This would be what? Because y equals x here? 2, 2. Oh, I see. Y is going from 0 to 2. No, it's not. No, it's not. Y is not going from 0 to 2. Y is going from what? 0 up to whatever x is. Okay? It's going from 0 up to x. Okay? Now, do you guys see, if I actually perform this integration, whatever f of xy is, if I perform this integration, right here, I will end up getting what? A function of x. That will end up giving me a function of x. The main thing to notice here, that is not a constant. You're not going from y equals 0 to 2. Okay? You're going from whatever y starts at 0 but goes up to whatever x is. Okay? Now, what about the y? Oh, wait. Where are the y values going here? Or the x values going? Oh, yeah, the x values are going from 0 to 2. I am partitioning from what? 0 to 2. Okay? Let me give this thing a name, by the way. I'll call it I. Okay? Now, usually people would write this. And now, this is just in the beginning. You know, we're learning. And just for emphasis here. You go from what? 0 to x, 0 to 2, f of xy dy dx. Okay? That's important. Okay? Now, let's talk about what if I turn this around and I go in the x direction first. So I'm changing the order of integration here. So I'm still going to go y or I equals. Okay? Now, I'm thinking of it this way. I'm going to come over here in my drawing, and I'm going to leave this other little partition there, a little picket. I'm actually thinking of integrating in the x direction first, so I'm coming like this. Okay? I imagine this being divvied up like that. Okay? Now, all right, so I write my double integral. F of xy. I'm integrating out x first. Okay? Now, let's come here. I should have maybe mentioned this before. Hey, is the region I'm integrating over a rectangle? No, it's a triangle. Therefore, what? At least one of these inner limits here on this is going to have to be variable. If on the outer limits, they're always going to better have constants if you want a number for an answer. Okay, these are going to have to be constant up here. That's no question. How about out here, though? No, at least one of these is going to have to be variable. Otherwise, you'd be integrating over a rectangle. Would you or not? Okay, now hold it. Now, what am I going to be looking for here? I'm going to be integrating out y second here. Okay, now hold on. What's the limit? Oh, wait, the upper limit's really easy on this. I'll jump in there first. X equals 2. But, well, what's the lower limit on x here? Well, the lower limit on x is this line. So it's actually x equals y. Ah, that's variable. I'm actually going from y to 2. Now, once again, emphasize here. You guys see here, when I integrate this out, whatever the f of x, y is, when I integrate that out, I'm going to get what? A function of y. And then I integrate that and get a number in the end. Okay? I get a number in the end. Let's get these off here. So x isn't going from, again, what's a common error? X goes from 0 to 2. Yeah, x goes from 0 to 2 all the way down here. It goes from 2 to 2 up here. Where does it go in general? From y to whatever to 2. Okay? So let's come over here. Now, what about my y values? Now, these are going to have to be constants here. Y is going from, as you can see, from 0 up to what? 2. Now, again, I don't like writing it this way every time. Here's what we end up doing. And I'm going to start doing this from now. Okay? F of xy dx dy. X is going from what? Y to 2. And then from what? Y is going from 0 to 2. Okay? So, if I have any continuous function of two variables and evaluate these two different ways, I'm actually going to get the same answer out of these two. Okay? Exactly the same answer. All right? Now we're going to do more of these as time goes on. Got to get this down.